Okay, so we're on page 21. More of that stuff that we did yesterday. Now this next problem is going to be a little different, but actually you're going to see, hopefully you're going to see that this is actually a pretty easy one once we know how to deal with this. The sine of pi over 2. What quadrant is pi over 2 in, or is that just a bad question?
It's 90 degrees.
It's 90 degrees. Okay, so I'm going to go draw this thing. I know that pi over 2 is the one that goes straight up like this. So here's my angle of pi over 2. There's my pi over 2. I cannot make a right triangle with the x-axis that uses this 90-degree angle, because then I'd have like another 90-degree angle somewhere else. But watch what we can do with this. Do you know the length of this thing? 1, because we're on the unit circle. I actually feel like that's all I need to get the coordinates of this point up here. We're on the unit circle. It's always 1 with these. The radius, the we're not hypotenuse anymore. The radius is 1. We're not making a triangle. Not 1, 0. The coordinates of this point are 0, comma 1. Yes, which we're going to get to. Yes. So now, I don't actually need a triangle for this. I have an x-coordinate. I have a y-coordinate. What's the r, by the way? 1. It's always 1 with these problems. I have everything I need to find the sine of pi over 2. Well, the sine is the y-coordinate, which is 1, over the radius, which is 1. We're going to get 1. If we have an angle that is 90 degrees or 180 or 270 or 360, we're not actually going to draw a right triangle. We know the radius is 1, so I can get the coordinates very quickly. It's either 1 or 0 or some version of that, maybe some negatives. And then I can use my x, y, r formulas. Let's do letter H together, and then I'm going to let you try I and J on your own.
So that's our final answer?
That's the final answer. The sine of pi over 2 is just 1. And we're actually going to see in a little bit, this is actually going to be important for our graphing stuff that we'll deal with in a little bit. Next, letter H. The cosine of 3 pi over 2. Where is 3 pi over 2? Yeah, so the one that goes like straight down. So here's my 3 pi over 2. And I know my radius is 1. Raise your hand if you can tell me the coordinates of that point. Don't just say it out loud. Raise your hand if you think you have the coordinates. Do it up.
R equals 1, x equals 0, and y equals -1.
Good. The coordinates are 0, comma, -1, because I'm not moving left or right at all. I'm just moving down. No, Katie? Are you okay with me having the point over here? I didn't move left or right at all. I just moved down 1 unit. 0 for the x, not moving horizontally, -1 for the y.
You moved down 2?
No, because we're on the unit circle and our radius is always 1. So we've got the x, we've got the y, we've got the r. What's the cosine going to be? 0. The cosine is the x-coordinate, 0, over the radius, which is 1. The cosine of 3 pi over 2 is 0. If it is an angle that is right on an axis, you're not going to draw a triangle. I actually think this is much easier than just drawing triangles. You know the radius is 1. You know you've gone out 1. Get the coordinates involving 1s and 0s or -1s, and then use your formulas. Try I and J right now on your own. And don't go beyond that yet. Please don't go beyond j. Bless you.
I got a question.
What's your question?
If
So we'll talk about j in just a moment. Something a little strange is going to happen in j. Sam, do you have an answer for I?
0.
0. Good. Pi is the angle that takes you over there. I know my radius is 1. I know the coordinates are going to be negative 1 comma 0. Well, the sine is the y over the r, so 0 over 1, sine of pi is going to be 0. Pi over 2 is the angle up here. What are the coordinates of that point? 0, 1. Actually, we did the same thing in letter G. Raise your hand if you can tell me the tangent. Jalen. Undefined. We are doing 1 divided by 0. This is kind of strange, but you know you can't divide by 0. So actually, the tangent of pi over 2 is undefined. If you went to your calculator, first of all, do you see how I got the 1 over 0? And then 1 divided by 0. You can't divide by 0. If you went to your calculator in degree mode and said the tangent of 90, it would say undefined. Or if you went to the calculator set in radian mode and did the tangent of pi over 2, it would tell you undefined. Or it could say error, or I think some of the graphic calculators might say divide by 0 error or something. Sine and cosine will never be undefined because we've got a radius and radius is always 1, but tangent might be. Do I need to explain?
No, it's just.
Yes.
Question? Okay. Next. The sine of negative, so we've got to deal with some negative angles now. The sine of negative 5 pi over 6. First of all, we're going to convert negative 5 pi over 6. What's regular 5 pi over 6 in degrees? 150 degrees. So the sine of negative 5 pi over 6 is just the sine of negative 150 degrees. I want to do k together, and you'll try L on your own in a moment. So, the sine of negative 150 degrees. Let me draw this thing. Where is negative 150 degrees? What quadrant, first of all? 2, 3, 4, I've heard. Okay. So let's look at this. I know that positive 150 degrees is the angle that looks like this. So negative 150 degrees needs to spin the same amount in the opposite direction. So negative 150 will be spinning somewhere over here in quadrant 3. Spin the same amount, but in the negative direction. Negative 150 degrees will look like that. Now, I'm going to go and make my triangle. Okay. If this was negative 150 degrees, and this is negative 180 degrees, what positive, like normal good angle must you have in between?
30.
30. I'm going to fill in a 30 there. And actually the rest of this problem is nothing new at all. See if you can finish off K. Fill in your sides, get your coordinates, find your sign. We'll stop and check, and then once we're good, you'll move on to L.
So, I'm assuming like the things for triangles,
Yep.
for the base of 90, we always go the x-axis.
Let's leave those alone, please. Always with the x-axis, yes.
No, like,
The triangle is always a triangle that you make with the
no,
x-axis.
not that, but like, to find the degree, we always go like, how much it is.
To the x-axis, yes. Michael, do you have a final answer for k?
-1/2.
I like that. Your coordinates should have been negative root 3 over 2 comma negative 1/2. The sign is the y coordinate, negative 1/2 over the radius of 1. You should have negative 1/2 over there. So really, negative angles, once we have the thing drawn, we've spun a negative direction to get there. You figure out how much more you need to get to an axis, figure out the angle in between, and then it's like what we were doing yesterday. You go try letter L right now on your own. The tangent of negative 120 degrees. You know what quadrant you're going to be in?
Three.
It is 3 once again.
3. Got it.
Please do it.
Now I'm getting mixed up.
That's alright.
By what?
When I do 180 minus 120, it's like
Okay,
equals 60,
so
or-
so let's not think about signs at the moment. Let's just think about actual degrees, I guess. If this is 120,
yeah.
and to get there is 180, how many more degrees do you need to get from 120 to 180? That's 60.
Yeah, but that one time it was like different.
I don't think so.
Yes.
I think this is no.
Keep going.
Is there like trick going into this? Besides just literally.
You know what the positive is. Go the same amount in the negative direction. That's the trick. So it's not really.
There's no positive, but it doesn't use axis. That's not.
Be careful though. It has to be the x-axis that you would flip the thing over.
See, that's what I was thinking. You know,
Shh, shh, shh. You can. Or forget what I just said and do your multiply by the reciprocal to finish things off. You'll get the same answer. Do we have negative 1/2 comma negative root 3 over 2?
Yeah.
Maybe. The tangent is the y over the x. Negative root 3 over 2 over negative 1/2. Negative, so first of all, negative root 3 over 2 divided by negative 1/2 is the same problem as negative root 3 over 2 times negative 2 over 1. Cancel the negatives. Negative times negative cancels.
Root 3.
The 2's are going to cancel. We're going to get root 3 for the tangent of negative 120 degrees.
Oh.
Questions here?
We don't need it, so that's how
If you went from here to root 3 because you can see the negatives cancel and the 2's cancel, that's okay as well. Okay. One more well, actually 2 more variations we need to deal with. M, the cosine of 13 pi over 6. Where's that? Above what? Okay.
Goes around once.
So here's the deal. This is bigger than a whole time around the unit circle. Whole time around the unit circle is how many radians? So first of all, normally what would we say? 1 whole time around the unit circle.
215.
2 pi is 1 whole time around the unit circle. If we were talking about an angle over 6, isn't 2 pi 12 pi over 6?
375.
Hold on. 12 pi over 6 is 1 whole time around the unit circle. This is too big. What we're going to do with angles that are bigger than 2 pi or bigger than 360 or less than negative 360 or less than negative 2 pi is we're going to find a coterminal angle. The angle that basically spins around the same amount but not having gone around that extra time. What I need to do in M is I need to find a coterminal angle. I'm going to find a coterminal angle that is something around the x-axis. Where did you just get pi over 6, Philip, from? So let's do that. I've got 13 pi over 6. We can subtract 2 pi, but getting a common denominator, 2 pi is 12 pi over 6. Yeah, I would love. This is not a difficult angle. For other angles, though, yes, you will need to. So I know that pi over 6, well, first of all, the problem has now become the cosine of pi over 6. And pi over 6 is what in degrees? 30 degrees. So here's why what I just did is allowed. If I now draw a 30-degree angle, 30 degrees is that. If instead of a 30-degree angle, I drew a 13 pi over 6 angle, that angle would look like this. It would still end in the same place. I don't need that extra spin around the thing. My reference angle for that bigger thing would still be the 30 degrees. That's why we're allowed to change the problem to sine or cosine tangent of a coterminal angle. I think that's all I need to say. We've got a 30-degree angle there. Find the sides, fill things in, get your positives and negatives, and go. And when you're done, do letter N on your own as well. Again, it's too big. You'll need a coterminal angle in degrees that time. Try both M and N. Yes, you do, because it's bigger than 360. I'm not doing this great. I would recommend making your drawings large so you can fill angles in and stuff. I'm going to try to do N bigger. Once you finish M, go do letter N.
Are we going to go over any more of the, like the first ones where it's like those items on the axis?
Say that one more time.
Are we going to go over any of like the first 4?
Yes. Yes, we will. I would like to see how you're getting it. I do want to see that. I would like to see that. If you show it, you will definitely not lose points. If you don't, I don't know. Josh, do you have an answer for letter M? Good. Your coordinates at that point should be root 3 over 2, comma 1/2. I want the cosine, so the x-coordinate, root 3 over 2 over the radius of 1. You're going to get root 3 over 2. Good. Evan, do you have an answer for N? Good. What were your coordinates?
Negative root 2 over 2, comma 2 over 2.
Good. And then we'll do our sign, the y coordinate, root 2 over 2 over 1, root 2 over 2. So I found a coterminal angle. I subtracted 360, got 135. So the sine of 495 degrees is the same as the sine of 135 degrees. There was more I wanted to say about this. Okay, so I've got my 135. This is 135. How much more do I need to get to the x-axis? Well, 45 degrees. So it's a 45, 45, 90 triangle. 1, root 2 over 2, root 2 over 2. Get the coordinates and go. I feel like K through N is truly as tough as this chapter gets. Questions? There's one more piece in section 9.3, so I guess we should take a look at the next page. Trigonometric functions of what we call quadrantal angles. Honestly, we already did this. We didn't call them quadrantal angles, but we're going to do this. Quadrantal, what like math word is in there? Quadrant is the word that I was talking about. These are angles that lie not in a quadrant, but in between quadrants, so on an axis. Quadrantal angles are angles whose terminal ray is on an axis in between quadrants. There are 5 particularly important quadrantal angles. I don't even feel like bothering with this in degrees. We'll just do this in radians. 0 radians is a quadrantal angle. Pi over 2 is a quadrantal angle. What's the next quadrantal angle? Pi. And then 2 pi, which ends in the same place as 0. Well, here's what we're going to do with these. To make some problems go quickly, and Jack, this is actually what you were asking about, the more practice with those angles that lie straight up or straight over. I know the radius is 1. I might as well fill in radius of 1 everywhere. What are the coordinates of 0 or 2 pi? What are the coordinates of the angle over here? 1, comma 0. I'm moving horizontally 1. Bless you. I'm not moving up or down. Coordinates are 1, 0. What are the coordinates of pi over 2? 0, 1. Take a moment, get the coordinates for pi and the coordinates for 3 pi over 2. And once we have those, it's actually going to make the problems on the bottom pretty quick because we have all the coordinates we need. We just need to pick out the specific things. Robbie, what are the coordinates of pi? Negative 1, 0. Good. And Natalie, how about the coordinates of 3 pi over 2? 0, negative 1. Do you see where those came from? We're going to start graphing in just a moment. These angles are going to be the most important angles for our graphing. More with that in a minute. Which I think is what Natalie said, and now it's what I have written, 0, negative 1. I would like you to do the problems on the bottom of the page. Find the sine of pi, the tangent of 3 pi over 2. Well, you already have the angles. You already have the coordinates. Go to the right angle. Pick out the right coordinates. You know your radius is 1. Finish this off. Try those 4 problems quickly right now. Olivia, do you have an answer for the sine of pi? Well, those are the coordinates. So now we need to go and use our sine formula. The sine should be the y-coordinate over the radius. So what's your y-coordinate at pi? 0. What's your radius? Always. So what's the sine of pi going to be? 0. That's what you're going to do. The negative 1, 0 are the coordinates, but then we have to use them with our sine, cosine, tangent formulas. Kayla Soldi, do you have letter B? Undefined. Good. Why? What were you doing? Good. You were doing the y-coordinate over the x-coordinate, negative 1 over 0. That is undefined. Byron, how about C, the cosine of 2 pi?
1.
Good. We should be doing x-coordinate is 1 over the radius of 1. 1. And Eva, how about D? 1. Y-coordinate is 1 over 1. Questions here?
No.
Okay. We are going to start looking at some graphing with sines and cosines. And actually what we're about to do will be the final 2 graphs for our library of functions. We need to look at what a sine looks like and what a cosine looks like. Tangent, we're going to save for next room. On the next page, we want to graph the sine of x. Y equals the sine of x. And I need to plug in some good x values. Now, my good x values are angles that I can easily find the sine of. I am not going to plug in 0 and 1 and 2 and 3 and 4. Philip. I'm going to plug in like those quadrantal angles, like the ones I just dealt with, because finding sines of those angles I just dealt with are really easy. I want to find the sine of 0. I'll do that in a moment. I want my next x-coordinate to be pi over 2, which looks really weird, but if you look at how I labeled the x-axis, yeah, there's a pi over 2 there. That's okay. Then pi. Then 3 pi over 2. Then 2 pi. So, my y-coordinate is going to be the sine of 0, the sine of pi over 2, the sine of pi, the sine of pi, the sine of 3 pi over 2, and the sine of 2 pi. I think you could figure out those 5 problems using what we just kind of did on the previous page. Go to the previous page. Let's find the sine of 0. And I want to say this. Okay, right now I'm using x's and y's for graphing. I had x's and y's on the previous page. They're different x's and y's. They're x's and y's for the unit circle on the previous page. Not the same that I'm dealing with here. So the sine of 0, you're going to go to the previous page. You're going to do your y-coordinate over your radius, which is 1. What is the sine of 0, by the way? The sine of 0, going back to that previous page, the y-coordinate over the radius, y-coordinate was 0, radius was 1, sine of 0 is 0. I'd like you to use that previous page again to find the sine of pi over 2, the sine of pi, the sine of 3 pi over 2, the sine of 2 pi, and stop. What's the sine of pi over 2? Just say it. What's the sine of pi over 2? 1. I'm looking at pi over 2 on my unit circle. When I'm on the unit circle, the sine is the y-coordinate divided by the radius. Y-coordinate is 1. Radius is 1. 1 over 1. The sine of pi over 2 is 1. Sine of pi? 0. Sine of 3 pi over 2? Negative 1. Sine of 2 pi? 0. I'm going to plot those. This is kind of strange. I've got 0, 0. I have pi over 2 comma 1. I have pi comma 0. I have 3 pi over 2 comma negative 1. I have 2 pi comma 1. It's like going up and then down more and then up. Hold on one moment. I feel like I need a little bit more to actually understand what's happening though. Negative pi over 2. Well, going back to our unit circle. If this is pi over 2, isn't this angle negative pi over 2? What's the sign there? What's the sign down here at negative pi over 2? Negative 1. Negative pi. What's the sign of negative pi? 0. It's going to keep like repeating and bouncing. I'm going to get a 1. I'm going to get a 0. Now, to connect these, I'm not going to use line segments with sharp turns. If I actually plotted a few more points, like pi over 6 and pi over 4 and pi over 3 and the good things around the unit circle, it would end up looking something like this.
Oh, why'd you start in the middle?
Why not?
Because
Because that point was 0, 0, and that's always a nice point to start at. My graph of the sine of y equals the sine of x is going to look like that.
it's like a mountain.
Okay. As it continues to the right, is it just going to keep going up forever? What's it really going to do? It's going to keep bouncing. It's going to keep bouncing between a highest value of 1, a lowest value of negative 1. In a couple days, at the very end of this unit, we will talk about why these things are important. But basically, anything in the real world that repeats with a pattern like this can be modeled using sines and cosines. So we're going to talk about how, like temperatures that repeat over the course of a year. We have a low temperature maybe in January, a high in June, and then the next year it repeats and a low the next January, a high next June, or July, or whatever. We can use a sine or a cosine that we'll see in a moment to model those things and to predict what the temperature might be in April and May, things like that. Katie. Not next week, early the week after. Preston. Not yet. Not ready to do that quite yet. Domain. What is the domain of this? Yeah, we're going left forever, we're going right forever, all real numbers. The range is kind of strange, though. The range is the y values. Are the y values all real numbers? No. Raise your hand. This goes like way back to the beginning of the year. We did look at some of these, though, in the beginning. Raise your hand if you have an idea. Josh. Yes. So, well, first of all, not less than, but less than or equal to, because we actually do reach those ones and negative ones. I'm going to use a compound inequality for this. Going back to how we dealt with this in the beginning of the year, we would have said negative 1 is less than or equal to y is less than or equal to 1. Philip. Nothing. Nothing involving sines and cosines. To get straight lines, you'd have to do something that we're not going to deal with right now. Okay, I want to skip those next two words. We're going to define those tomorrow, but I do want to get the graph of the cosine of x. On the bottom of the page. What x values am I going to plug in? The same ones I plugged in last time. I'm going to plug in 0. I'm going to plug in pi over 2. So you can follow this better. I'm going to plug in pi. I'm going to plug in 3 pi over 2. I'm going to plug in 2 pi. So I want to find the cosine of 0. I want to find the cosine of pi over 2. I want to find the cosine of pi. Cosine of 3 pi over 2. Cosine of 2 pi. I would like you to see if you can do this on your own for the moment. Go back to the previous page with that unit circle with those quadrantal angles. Get your cosines of those angles. The x-coordinate of the radius, which was always 1. Try those. And I guess when you're done, you can plot them, but don't connect them yet, because we got to talk about the negatives and just make sure that works out properly. What's the cosine of 0? I think it's 1. When we're at 0, it is our x-coordinate over the radius. X-coordinate is 1. Radius is 1. 1 over 1. Cosine of 0 is 1. Cosine of pi over 2. That is 0. Cosine of pi. Negative 1. Cosine of 3 pi over 2. 0. Cosine of 2 pi. Okay, so 0, 1. Pi over 2, 0. Pi comma negative 1. 3 pi over 2 comma 0. 2 pi comma 1. So I've got some points. It still looks like it's kind of bouncing, but kind of in a different way maybe. So hold on. Now let's go negative. Negative pi over 2 is over here. What's the cosine of negative pi over 2? 0. Negative pi is this angle. Negative 1. Do you see the pattern still kind of repeating here? What's going to be next? Sorry, what's negative 3 pi over 2? 0. What's negative 2 pi going to be? If we connect these, it will look something like that.
Big W.
Sure.
Elixir.
Does anyone notice something about this graph compared to like the sine graph?
Nope. It's moved more to the left.
It kind of looks just like the sine, but shifted a little bit. They are going to have the same like basic idea of bouncing between different values. They're just kind of starting in a different place. More with that next time. But quickly, I would like you to figure out your domain and your range for the cosine.
Yes.
Maybe. Domain.
All numbers.
Range. Yeah. A couple comments. First of all, have you actually seen things that look like this before?
Yeah.
Like where?
Over there.
Gale Preston.
I've seen it.
Gale
Okay, beginning of the year when we were kind of doing domain and range things. Have you ever seen pictures of like sound waves and things that? Yeah, those are all based on sines and cosines. Why? Not yet. I need a few more days to get there, and then we'll kind of talk about that stuff. Yeah, and like the picture on the graphing calculator up there. Couple comments. Please, this is important. Next class, we're going to be doing a lot more with the graphing. We're going to change these. We're going to stretch them. We're going to compress them. We're going to make them go up and down and all that. Because we're going to do more with graphing, you need your colored pencils. Quite honestly, what we're going to do next time is actually going to be pretty easy because you already know the basics of how to change our graphs. But make sure you bring the colored pencils. There is no graphing in the homework tonight. Let me shut this off.